Hi everyone, my name is Tuan,
Hi, I'm Haofan.
and we are PhD students here at the University of California, Santa Cruz, advised by Owen Arden. Today we will be presenting our work, detecting Eclipse attacks from inside trusted execution environments. The trifecta of information security guarantees are confidentiality, integrity, and availability. And this is what we want in distributed applications. There are some techniques that can help us achieve this, for example, trusted execution environments or TEs and blockchain. In blockchain applications, components publish data or computation to the public chain, and other components can query the result from the chain. This provides us with availability because, in our case, even if host 1 crashes after publishing, host 2 can still query the result from the chain. We also get integrity because all data on the chain are immutable. We don't get confidentiality here because data and computation on the chain are all public. TEs allows us to define protected memory regions in which we can run our components. This provides us with confidentiality and integrity because computation done inside the TE are safe from unauthorized access, even from privileged code in the host OS. However, we don't have any availability guarantees because the host has full control over the network stack and can suppress, reorder, or replay messages coming into and going out of the TE. A strawman solution that utilizes both techniques consists of components doing some confidential computations inside the TE and then publishing the result to the public chain, after which other components can query the result. On the surface, it looks like we have achieved all three guarantees, but this is not the case. We are still faced with the problem that the TE cannot guarantee that the data from the host is received. Because of the position of the host on the TE, having full control over the network means that the host can perform an Eclipse attack, where it selectively delivers information that it wants to the TE. An attacker can use this technique to undermine the integrity and availability of C2, and if successful, can in turn affect anything that relies on C2, possibly the entire application. If an attacker has a significant amount of hash power, in addition to being able to suppress time-sensitive information, it can also generate its own malicious blocks on its fork of the chain. An attacker can convince the TE to accept these blocks. It may cause the TE to disclose secrets. This problem of an Eclipse attack in blockchain applications with TEs is hard, but before we get into the solution, let's first revisit some of the characteristics of a blockchain, specifically a proof-of-work blockchain. In proof-of-work, nodes in the network compete to solve cryptographic hash puzzles. The first to solve a puzzle gets to propose a block that gets appended to the end of the blockchain. Nodes in the network have an expectation of when these blocks should be arriving, and this expected block time in turn influences the difficulty of the next blocks to be generated. We make another assumption of this minority attacker, where a single entity should not be able to attain more than 51% of the hash rate. Our solution relies solely on these assumptions to detect and mitigate Eclipse attacks. An Eclipse attacker has three options. When it sees a block on the public chain, it can either deliver the block to the TE, in which case the TE functions normally. It can choose to delay or withhold this block, but detecting this is trivial because we can simply rely on the block timestamp and the elapsed time. Or it can fork its own chain to generate malicious blocks. And there are two problems with this. The first is that even though the attacker cannot forge transactions from keys it doesn't have access to, it can choose to discriminate certain transactions and even roll back transactions that's already been confirmed on the main chain. The second problem is that because this fork is generated by an attacker with a minority hash power, the blocks will be in decreasing difficulty because of the rate at which they're being generated. If the attacker can convince the TE to keep accepting these blocks, then the difficulty will reach a point where the attacker can sustainably generate these blocks in a timely manner. Detecting this type of attack is not so straightforward, and Haofan will now explain why the block difficulty is useful and how we use it to detect this type of attack.
So why difficulty is useful to us? That's because we assume attacker has minority hash power, so it will take more time in average to generate malicious blocks. A higher average block time will lead to lower difficulty value. So to detect malicious fork, we can monitor the change in difficulty value. And by comparing the difficulty value in the new block to a reference value, we can determine if the new block is malicious or not. However, we need to take the nature difficulty fluctuation into consideration when determining the reference value. This figure shows the nature fluctuation in real Ethereum blockchain. Miners may join and leave the network over time, causing significant increase and decrease in difficulty value in the long term. Therefore, we can't just rely on one reference value for all the blocks. Meanwhile, comparing the change between two blocks that are next to each other is not enough. As shown in the example difficulty fluctuation chart, the difficulty value may drop at some points during normal fluctuation, while the attacker may try to slightly decrease the difficulty each time, and after a series of blocks we can see a significant drop accumulated. Thus, we need to monitor the difficulty value in some series of blocks. To adjust the reference value, we group blocks into fixed-sized checkpoints. The median value from the checkpoint 1 is selected as the reference value. Next, the minimum difficulty value is calculated based on this reference value and compared to the new blocks. Once there are NC blocks found in the front, the previous candidate checkpoint will become the new checkpoint, and the new NC blocks become the new candidate, and the minimum value is updated accordingly. In order to evade the detection, an attacker will have to continuously produce at least the NC blocks without dropping the difficulty below the minimum value. That's really hard for the attacker to break the system. But exactly how hard is it? The possibility of the occurrence of such an event is referred to as the false negative rate. We calculate the false negative rate based on a formula constructed with exponential distribution of block arriving time. For most of the parameters we chose, it will be as easy to brute force someone's secret key as to evade detection by our monitor. Next, we evaluate the false positive rate with 10 million historical blocks in Ethereum. A false positive block is a block that triggers a detection by our algorithm, while the system isn't under an Eclipse attack. Although there are multiple false detections, almost all of them are caused by either hard fork, denial of service attack, bug fix, or API updates. During such an event, Enclave needs to be replaced by the latest software build anyway, so it isn't concerning to the application. In this talk, we discussed the importance of detecting Eclipse attack inside a blockchain application built with Enclaves. We then present a novel solution by monitoring the difficulty value in the proof-of-work blockchain. This monitor is inexpensive and immune to long-range attacks. It can prevent malicious forks and provide negligible false negative rates. And it's unlikely to trigger false positives. Thank you for listening to our talk, and we are happy to answer any questions you may have.